So in this part of the lecture, I'm going to discuss reduction of multiple subsystems, which covers your chapter 5. So first I'm going to start with a description of block diagrams and how to simplify block diagrams and how the block diagrams are, or how rather the blocks are connected to each other. Then I'm going to discuss how to reduce the interconnection of several block diagrams and simplify it in order to get a single block. Then I'm going to discuss the so-called signal flow graphs, which is an alternative to block diagrams. Then I'm going to talk about finally the Mason's rule in order to simplify a given signal flow graph. So this slide here shows you how the block diagrams could be connected. So first we show signals by just an arrow. For instance, this R of S, which is the Laplace transform of, let's say, input. So this is actually shown by an arrow. So this is just direction of the flow of the data. So it means that your system has actually an input R of S and the output is C of S. So, and again, this is how you would show the signals. Then here we have systems. So in systems, obviously it's a block, G of S. The input to it is R of S, and the output is C of S. So, so then we have the so-called summing junction, which is just this junction that you see here. So this junction takes as an input, for example, in this example, 3 inputs, R1, R2, and R3, and it produces an output. So in this case, you have an arrow R1, and it's the sign that actually enters this summing junction is positive. For R2 is positive, for R3 is negative. Therefore, the output C of S is going to be R1 plus R2 minus R3. Then we have a peak off point. So basically that's also a junction from which you have multiple points departing. Next, I'm going to talk about the cascade form of interconnecting multiple systems. For example, if you have the first system G1, the input to it is R, then the output of the first system, you can call it X2, but that's really G1 multiplied by R, and that's what you see. Then if X2 is the input to another system G2, we actually call G1 and G2 connected in series or really cascaded. So the output of G2 is going to be, let's just call it X1, which is G2 multiplied by X2. And X2, we already know that's G1R, and therefore X1 is going to be G2 multiplied by G1R, and that's what you see here. Then if this serves as the input to another system, let's just call it G3, the output of that third system is going to be G3, G2, G1, R of S. So really, if you represent the whole, the entire interconnection of these 3 systems that are connected to each other in a cascade form by just a single transfer function, let's just call it G of S, then that transfer function is going to be simply the product of the 3 transfer function, and that's exactly what you see here. So now really, if you connect multiple subsystems in a cascade form, the equivalent system is actually going to have a transfer function which is the product of all those individual transfer functions. So the next type of interconnection interconnection of multiple subsystems is the parallel forms. So in this case, you have a peak-off point here. So there are 3 signals departing from it, and so basically the same signal R of S serves as the input to 3 systems, G1, G2, and G3. So the output of the first system is just going to be RG1. For the second one, it's going to be RG2. For the third one, it's going to be RG3. So now, if you just add or subtract them using a summing junction, the result is going to be exactly what you see here. And therefore, you can replace this interconnection, this parallel interconnection of these systems by simply the sum or subtraction of this transfer function depending on how they enter this summing junction. So the next type of interconnection, or how the systems can be actually interconnected, which is the most important one that we are very much interested in this course, is the feedback for. So what you see in the first kind of figure here, so this figure actually shows the components of a feedback control system. So that's pretty much what you also saw in the first day, I did in the very first lecture. So this system actually has, so you have an input, or what we call reference input. So now this could actually represent the what we call input transducer. So the input, or your reference, could also have its own transfer function. And then we have here the plant that you're trying to control. And so the G3 is really the transfer function of your system, the open loop system. G2 is the transfer function of the controller. And then you have a feedback path that are actually taken from your output. So your output, your sensor can itself has an input, output transducer. So these two themselves actually can serve as the transfer function associated with the sensors. And also you can have a transfer function in the feedback path. And the E of S is what we call just the tracking error. And that's actually a signal that goes into the controller. So the next figure shows that if you just simplify this transfer function or this interconnection, so the first one, it's actually going to look like this. So the G here that you see is just an equivalent representation of the plant and the controller. So really the G is just G2 multiplied by G3. Then we have H, which is really just H1 multiplied by H2. So this is really just H1 multiplied by H2. And so now, if R of S is the input to this feedback loop and C of S is the output or the response of the feedback loop, so it turns out that you can replace the whole feedback path. And I'm actually going to show it here. So you can just replace this whole thing by simply this transfer function. And this transfer function is actually going to be only dependent, of course, on G and H. So it turns out that it's going to be either G over 1 plus GS or G over 1 minus GS. So how do you decide on the sign in the denominator? So it just depends on whether you have a what is called negative feedback or positive feedback. So for example, I'm actually going to derive this equation for a negative feedback. So for a negative feedback, as you see here, so in the negative feedback, this summing junction, the input to it from the input is plus, but from the negative path, it's actually going to be just negative sign. And of course, we can have either a positive feedback where the sign of the path from the feedback is going to be plus, or it can be minus, meaning that it's going to be a negative feedback. So for a negative feedback, which is much more widely used in engineering systems than positive feedback, so we have here E, which is really just, so that's E. So that's just the difference between R and the output of the feedback. So it's just going to be CH. So it's going to, so your E is really going to be R minus CH. So the E is actually going to be R minus CH. But now remember that, so C here itself, C of S, is G multiplied by E. So now if you replace E by R minus CH from this equation, you actually end up with this equation, C equal to G multiplied by R minus CH. So if you just then multiply G, so get C equal to GR minus GCH. So you bring in C from the right hand side to the left hand side, so it becomes C plus CGH, or you can just factor C out. So C multiplied by 1 plus GH equal to GR, and therefore your transfer function from the input R to the output C becomes what you see here. So your C divided by R is G over 1 plus GH. So now this is really what we call closed loop transfer function. So now all you need to do is just going to make some room. All right, so now if you have this configuration, all you need to do in order to find closed loop transfer function, if it's a positive feedback, if it's a negative feedback, it's just going to be G in the numerator here, and the denominator is going to be 1 plus G multiplied by H. And again, this is if this is a negative feedback. If it's a positive feedback, then your denominator is just going to be 1 minus GH. Everything is going to be the same except that your denominator is just going to be 1 minus GH. So I'm going to do a very simple example. So in this example, let's assume that you have an interconnection of multiple subsystems, and the goal is to find the transfer function from R of S to C of S. So really you're looking for C of S divided by R of S. So now let's just start from the left hand side. So if the input to this system G1 is R, then the output is then the output of the system is just going to be G1 multiplied by R. So now if here C of S is the input to multiple systems, to H1, to H2, and also to H3. So really the output of this H3 is just going to be H3 multiplied by C. For H2 it's going to be H2 multiplied by C, and for H1 it's going to be H1 multiplied by C. And that's exactly what comes to the summing junctions, to these three summing junctions. So really the output of the first summing junctions is just going to be G1R minus CH3, and so I'm actually looking at this. So the output of this second summing junction is going to be G1R minus CH3 plus CH2, and that's what you see here. So for this third one, the output of this third summing junction is going to be exactly what we had as the input to this third junction, G1R minus CH3 plus CH2. And then we have here minus CH1. So I'm actually going to have this. So now I'm going to make some room. All right, so now we have actually, so everything is just simplified to this. So that actually acts as the input to G2. And therefore, and since G2 and G3 are connected in a cascade form, then you can easily replace the G2 and G3 by just G2 multiplied by G3, and therefore the C, which is the output of G2 and G3, is just going to be the input, which is this whole thing, multiplied by G2, G3. So here, if you're just going to take what I just showed you here, if you're just going to take it and rearrange terms that have C on the right hand side, it's actually going to be simplified to what you see here. And if you're just going to factor, so basically you just have to bring the C to the left hand side, and then when you divide C by R, it's just going to be G1, G2, G3 divided by 1 plus this whole thing. That was. So now that actually gives you the equivalent transfer function for the entire system. So really this is, of course, much more simplified than just the interconnection of those multiple subsystems. So the next topic I'm going to talk about is signal flow graphs. So signal flow graph is an alternative to block diagrams. So but unlike block diagrams, which consist of blocks, signals, summing junctions, and pickoff points, a signal flow graph only consists of branches, which really represent the systems, something like this, or nodes, which represents the signals. So instead of 4 things, we just have 2. One represents the system, and one represents the signals. So of course these are actually shown here in this figures A and B. So a system is represented by a line with an arrow. That's what you see here. So the arrow actually shows the direction of signal flow through the system. And adjacent to the line, which you see here, we have the name of the transfer function. For example, here is g of s. So also a signal is a node with the signal's name written adjacent to the node. That's what you see here. So this figure C shows an illustrative example. So it actually shows the interconnection of a bunch of systems and also the signals. And of course, each signal is the sum of signals that flow into it. So for instance, here, as you see, V of S is equal to R1 G1, actually comes from this path, minus R2 G2, that comes from this path, plus R3 G3. And also we have a bunch of, you can say output signals. So C1 is really just G4 multiplied by V, C2 is equal to G5 multiplied by V, and C3 is equal to negative G6 multiplied by V. So the next thing I'm going to talk about is how to build signal flow graphs. So the figures in A and B actually shows the cascade representation or cascade form, C and D parallel, and F feedback. So now, as an example in cascade, you see that we have R, V2, V1, and C in figure A. So this actually represents the signals. So, and of course, what really connects each pair of signals is just going to be the systems, and that's exactly what you see here. For example, between R and V2 here, we have a system G1. Between V2 and V1, we have G2, and between V1 and C, we have G3. So if you really want to replace all this by just a simplified signal flow graph, it's actually going to look like this. So we just have as an input, so it's just going to be R of S, and the output is going to be C of S, and the equivalent transfer function is going to be just G of S, which is really just going to be the product of G1, G2, and G3. And we can actually do exactly the same thing for parallel interconnection. So R is the input, and then we have a bunch of intermediate signals, V1, V2, and V3, which are really the outputs of the first, so the outputs of the three subsystems, G1, G2, and G3, as you see here. And then we have C, which is the sum of 3, which is just simply G1, V1 plus G2, V2 plus G3, V3. Or rather, I'm sorry, C is just going to be G1R plus G2R plus G3R. And remember that V1 itself is G1R, V2 itself is G2R, and V3 itself is G3R. So really C is just the sum of V1, V2, and V3. And finally, for feedback interconnection, we actually have a very similar thing. So we have three signals. One is the R, one is your error signals E, and the other one is the C, which is the output. So now you see that we have R here, and it actually, the output of the R, which can be actually represented by just a signal R that passes through a system with a unity transfer function, or just transfer function of 1. So that is actually becoming an input to these E here. So really E is going to be R minus HC. And then this E is going to serve as the input to your G. So really your C is just going to be G multiplied by E. So there is an actual example that I'm going to discuss. So this example shows you how to convert a block diagram to a signal flow graph. So if you just consider this block diagram, so this block diagram consists of bunch of systems. So G1, G2, G3, H1, H2, and H3. So really there are 6 systems. So every signals. So if you're going to solve a problem like this, for every input and every output of every system, you have to define a signal, and those signals will be represented as a node in signal flow graphs. And each of these systems can be just put as a branch in that graph. For example, here, starting from left, we have R, and then the input to G1 is V1, the input to H1 is V6, the output of G1 is V2, the output of the summing junction is V3, another input to this summing junction, which is the output of H2, is V7, etc. So for all of this, we'll have to define signals. So now, the first step in converting a block diagram to a signal flow graph would be to just show how these signals are actually located with respect to each other, and that's what you see here. So now we start from R, then we have V1, which is actually associated with this point, then we have V2, V3, etc. So I mean, all of this you're actually going to see. So the next thing, which is actually shown in B, just represents how those signals or how those nodes of that graph are actually related to each other through branches. For instance, I mean, this is just as an example. For instance, between V6, which is right here, so I'm just going to make some room here. All right, so for example, between V6 and V1, you see that in order to reach from V6 to V1, you have to invert the sign of V6. So really, if there is just a way to represent the relation between V6 and V1 as a transfer function, it would be V, like that transfer function is just going to equal to -1, and that's exactly what you see here. And I mean, between V1 and V2, it's actually fairly simple because you just have a transfer function G1, and that's what you see. It's actually labeled adjacent to this branch. You actually see G1, and you can do exactly the same thing for all of them, and eventually you would simplify this, so you're actually going to come up with an equivalence signal flow graph of that block diagram representation, which is actually shown here in figure C. And of course, there are some simplification that I have made along the way. For instance, here I have H1 and then I have -1. So instead of these two, because these two are just like two systems that are actually connected in cascade form. So, and its equivalent transfer function is just going to be the product of the two, which is going to be -H1. That's what you see here. And the same thing here for connection of H2 and -1. So the equivalent of those two is just going to be -H2. And the equivalent of, here you have G1 and 1. The equivalent of this is just going to be G1.